In today's vehicles, drivers and autonomous vision stacks can only see directly visible objects. However, in this scene, the approaching pedestrian is not directly visible to the observer, as the black car is in the way. Existing approaches show that it is possible to image such hidden objects by analyzing at the indirect reflections of a visible scene part, such as the road surface. This task is called non-line-of-sight imaging, and it aims to recover the shape and albedo of the hidden scene parts. In addition to imaging, fast and accurate detection tracking is critical in real-world applications, such as autonomous driving, and this has to be done in real time. Successful non-line-of-sight imaging methods use pulse-illumination. A laser first emits light onto the wall. Some of the scattered light hits the hidden object and is reflected back to the wall. After a third time bounce at the wall, the indirect transport components are received by the time-resolved detector and recorded in the transient measurements. However, the real-world measurements are typically very noisy due to the quartic intensity falloff for diffuse scenes. Indeed, reconstructing 3D scenes from measured transients with severe noise is a challenging inverse problem. A large body of work has explored methods for non-line-of-sight imaging. This can be classified in methods that directly acquire time-tagged measurements using pulse lasers, or indirectly acquire temporal information relying on coherent illumination or amplitude-modulated light. Methods that just require an intensity image for tracking applications, and very recent work that aims to improve the accuracy of image formation models and scene priors. For the most successful pulsed methods, traditional filtering and optimization methods that use handcrafted naive priors are slow and use approximate forward models. Existing methods cannot learn priors as there are two critical missing parts: training data and model architecture. Existing capture systems are large, non-portable, costly, and require long integration time. As a result, the acquisition of large training dataset beyond a handful of scenes is impractical. Indeed, large-scale dataset for this task does not exist. Learned models also do not exist. This is because the underlying task of transforming measured transients in the temporal domain to spatial domain is challenging. Existing autoencoders tend to overfit, and there's no learning model that readily reconstructs the hidden scene with high resolution. In this work, we overcome these obstacles to propose the first high-quality neural method for time-resolved non-line-of-sight imaging. Our method leverages physical models to learn volumetric feature embeddings from transient images. We first extract features which are propagated through a feature propagation module that transforms temporal domain features to the spatial domain. Once the features are embedded in the hidden volume, a visibility network estimates a visibility map to project the volumetric feature. Finally, an image render network takes the projected feature map as input and predicts an RGB image of the hidden object observed from the wall. While a depth estimator uses the visibility map together with the projected feature map to predict a depth map of the hidden scene. We also leverage a view transformer to predict from multiple views. The entire network is trained with intensity and depth supervision. This is different from directly estimating volumetric albedo and density as in existing non-line-of-sight reconstruction methods. Because our latent volumetric features learn to encode information such as shape, occlusion, normal, and semantics. In contrast to existing hand-engineered algorithms, that do not utilize a learned prior and run on the orders of days. The proposed method allows for real-time runtime with low memory consumption. The proposed model also differs from encoder-decoder models, which we found do not generalize because of the missing 3D-aware model structure. In addition to non-line-of-sight image and shape reconstruction, the proposed model also allows for downstream recognition tasks by replacing the rendering network with a different head. For example, end-to-end classification or end-to-end object detection. To render hundreds of thousands of transient training images in simulation, we propose a novel rendering algorithm which runs in real time. We consider the following non-line-of-sight setup. After illuminating the diffuse wall, light is scattered at the object point P, and some light scatters back to the wall where it is diffusely reflected back to the detector. As a result, a single wall point integrates light over the hemisphere. We decompose the rendering process into individual indirect views that can be rendered using orthographic rasterization. We render each view with fast OpenGL rasterization and generate a corresponding intensity image. We utilize the alpha channel to store the indirect distance maps, which records the path travel time. In the whole rendering process, we sample 10,000 view directions, which are then averaged on the fly using a GPU kernel. Integrating all the view directions results in a steady-state capture on the right. The alpha channel travel time allows us to bin the indirect observations in the final transient image, which are color-coded here. After binning the time at each time bin, we generate a 256 by 256 by 600 transient image with time resolution at 33 picosecond within 20 milliseconds. Using our fast rendering approach, we render a training dataset using the ShapeNet, multi-class, and motorbike dataset as hidden object geometry. Here are visualizations of the simulated training data. As a result, we've created the largest dataset for non-line-of-sight imaging, consisting of 13 classes and about 6,000 transient images for multi-class dataset, and about 7,000 transient images for motorbike dataset. Here are non-line-of-sight reconstructions in simulation. Qualitatively, the proposed method reconstructs 2D images with clearer boundaries and more details. Quantitatively, the proposed method outperforms existing methods by more than 5 dB in PSNR. Here, we test the model's generalization ability on simulation data. Specifically, we train a model only on the motorbike class, shown on the left. On the right, we show test results on completely unseen classes, such as airplanes, chairs, and lamps, validating that the method generalizes to unseen classes. We validate on real data that the method generalizes to unseen experimental data. On the top left, we show an experimental transit measurement with substantial measurement noise. The corresponding scene is shown next to it. The proposed model, trained only on synthetic motorbike dataset, also generalizes well on realistic scenes. Note that these real-world examples are out-of-distribution examples compared to the training data. Synthetic motorbike dataset. We can see that the proposed approach shows fine object detail and does not suffer from reconstruction noise. The proposed method also effectively handles complex geometries and scenes with challenging occlusions. While reconstructions from filtered back projection and phaser tend to have noisy background. The proposed method does not amplify reconstruction noise. Note that such noise in other methods cannot be easily removed by a learned denoising network. To validate this, we train a 2D UNet denoiser on top of phasor predictions of synthetic motorbike dataset. As shown here, such learned denoisers struggle to distinguish scene content from unwanted low-frequency recovery noise, and hence destroy fine detail. This resolution chart shows that the proposed model recovers fine hidden detail, especially with low reflectance. The network also handles challenging scenes with varying reflectance. For example, this is a facet disco ball. For all these out-of-distribution things, the proposed method recovers fine detail and clear object boundaries. In addition to scene reconstruction, by replacing the 2D render network with different headers, the proposed method also supports end-to-end classification and detection. Here, we show classification results. We compare to sequential pipeline approaches that first reconstruct an image and then add a classifier on top. The proposed end-to-end method outperforms such sequential approaches by over 15%. We also test our end-to-end model on one experimental bike scene. The last row shows the confidence scores for each class, with the highest confidence of more than 66% predicting the scene as a motorbike. This validates the model's generalization ability. For object detection, the proposed end-to-end method also substantially outperforms sequential pipeline approaches that first reconstruct an image and then add a decoder on top. The object detector trained only in simulation also again generalizes to real data, as shown on the bottom. In summary, we propose the first neural reconstruction method for non-line-of-sight imaging. We achieve this by introducing an efficient transient rendering method, with which we created the currently largest training dataset for non-line-of-sight imaging, and a neural reconstruction method for non-line-of-sight imaging and recognition that generalizes exceptionally well to real data when trained only on synthetic data.